Imagine falling away from the sun, plunging so deep into the ocean that the light vanishes and the water pressure would buckle steel. At these depths, human biology fails instantly. Every environment on Earth imposes strict physical constraints that dictate survival based on an organism's level of hyper-specialization. Bizarre animal traits represent precise biological engineering, calculated to counter specific environmental pressures. To endure these conditions, evolution has developed radical mechanical and chemical workarounds. Understanding a creature's appearance requires looking at the specific survival challenge it was built to overcome. The open ocean is a massive resource, but it presents a constant physical hazard: exhaustion. Any creature exploiting this space must find food without succumbing to fatigue and drowning. Look at the albatross. It manages infinite flight through a specialized locking mechanism in the shoulder. Once the wings are extended, this structure holds them rigid without any muscle energy, allowing the bird to ride ocean currents for hours at a time. It sustains itself by drinking seawater, made possible by a salt-filtering gland located above the eye. This chemical strategy allows it to remain at sea for years without needing fresh water. Coastal birds like the cormorant face a different set of physics. Their goal is hunting underwater, which means they must find a way to navigate without fighting their own natural buoyancy. While most birds rely on hollow, airy bones for flight, the cormorant evolved thick, solid bones. This density serves as a heavy ballast. It allows the cormorant to sink rapidly and chase prey underwater with high-speed agility. Locked zero-energy wings and solid bone ballast represent two distinct physical strategies for extracting resources from the same ocean environment. In the rainforest canopy, the constraints change. Navigating widely spaced food sources is dangerous, as the forest floor below is teeming with predators. The Draco lizard overcomes this by repurposing its own anatomy. When it leaps from a tree, it snaps its structural ribs outward symmetrically. These extended ribs function like the metal struts in an umbrella, stretching skin membranes into temporary wings. This allows the 8-inch lizard to glide distances of up to 30 feet, moving from tree to tree without ever touching the ground. By turning its internal skeletal structure into a parachute, the lizard completely bypasses the threats waiting on the forest floor. Consider the ocean floor at 1,000 meters. The constraints here are absolute: darkness, crushing pressure, and extreme scarcity. To function in total darkness, the giant squid uses extreme sensory scaling to capture every available trace of light. Its eyes grow to 30 centimeters in diameter. These massive sensors are designed to detect the faintest flashes of bioluminescence in the deep. To move through high-pressure water, it uses a specialized funnel beneath its mantle. By pumping water through this structure, it creates jet propulsion powerful enough for rapid strikes. But for scavengers on the seafloor, the challenge is different. They must extract nutrients from sunken whale skeletons, solid bone that can't be chewed or swallowed. The zombie worm solves this chemically. It uses root-like skin structures that secrete a powerful acid, which dissolves the bone and allows the worm to access the nutrients stored inside. Since the worm has no mouth or stomach, it relies on internal bacteria to digest the fats and oils its roots extract from the bone. Even its reproductive cycle is built for efficiency. The visible worms are all female, while microscopic males live their entire lives inside gelatinous tubes on the female's body. In the deep sea, survival requires abandoning standard biological rules. Mouths, stomachs, and even standard body sizes are discarded to minimize energy use. The locking wings of an albatross, the umbrella ribs of a Draco lizard, and the zombie worm's acid-secreting roots are all measurable reactions to physical forces. An animal's physiology is a physical map of the forces surrounding it: gravity, pressure, and light. The environment is the mold, and the animal's form is the cast. As we explore further into the deepest trenches of our planet, we can expect to find even more radical biological solutions to these extreme pressures. To see how nature solves the rest of Earth's physical challenges, subscribe and join us for the next breakdown.